So this is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate, but please do not share personal information during the class session. So at this point, we should have our ticket open. Password is in the chat box with the link. Again, this is only provided in class, so if you are watching a recording, you cannot get the password in the recording and you're missing out on 10% of your grade. So make sure you're coming to classes. No worries. Thank you, Mike, for getting back to me. All right, so we've got 22 days left of quarter number one. The countdown is happening rapidly. Guys, next week, we're going to be in the teens, okay? So it's coming to an end faster than you think. So today, though, we're taking a look at designing a Thermos Lab. I retook a look at this lab and I decided this one's actually way easier than Tuesdays. All right, so this one is actually super easy and it's short enough I can actually show you how to do everything in class. So it's a super easy one. So definitely do this one, definitely get it done because it's very, very simple. Tomorrow we have an extra credit game day. So make sure you come to class tomorrow so we can go ahead and do some review and get some extra credit. We definitely want to do this review because you do have your midterm exam. You do have your midterm exam coming up next week. All right, so that's why we have been doing all of these review days to make sure we're ready for the midterm exam. Awesome. Smiley faces if that makes sense. Confusion faces if we don't understand anything on our schedule. All right, looking good. Okay, so we have been talking all about energy. We talked about potential and kinetic energy. We talked about heat energy. Now we're going to be applying some of our knowledge in a lab. Okay, so today we should be able to, again, be able to describe how heat moves using conduction, convection, and radiation. And we should know the difference between conductors and insulators. This is mainly what our lab is about, talking about insulation. All right, so let's do a very, very quick review. Remember, the kinetic theory of motion says that the motion of particles is what causes heat. So hot objects have fast particles. Awesome, thank you, Ariana. And cold objects have very slow particles, right? Fast particles because they have lots of energy, slow particles because they have very little energy. Now, we do remember that the conservation of energy that we've been talking about says that energy is never created and never destroyed. So heat energy is never lost. It actually just moves from place to place, or it changes, right? And we talked about the three different ways in which heat can move. So we talked about conduction, right? We talked about conduction, convection, and radiation. So conduction, right, is when the two objects are touching and the molecules of one object are colliding with the molecules of the other object and transferring their heat. And remember, this always happens from hot to cold, never in the reverse. Because remember, when we say this phrase, is it better to say that you're letting the cold in or you're letting the heat out? Which makes more sense in terms of what we've been learning? Letting the cold in or letting the heat out? Tell me which makes sense based on what we have learned so far. Yes, totally, letting the heat out, right? Because really, heat is the only thing that can travel because cold is not a real thing. Remember that cold is actually just the absence of heat. It is not a real thing, okay? It's just an illusion. Not really, but you understand what I'm saying here, okay? It's not its own type of sensation, okay? Now, convection, on the other hand, convection has to do with those, what we call convection currents, right? That warm fluids will rise, right? Just like hot air rises, and cool fluids will sink. So cold air will sink. And as air is rising and sinking and cooling off and sinking and warming up and rising again and over and over and over, this mixes up the fluid and it spreads out the heat because we are using those currents to mix everything up. Smiley faces if these two make sense, right? Conduction is from touching, convection is from fluids. And then yes, radiation is kind of our special one. Radiation actually doesn't require any matter, right? It doesn't require solids, liquids, or gases, no atoms at all, but it can still transfer heat energy because of what are called electromagnetic waves. And remember, sunlight can do this, fire can do this. Again, we can get heat from those without there ever actually being any matter in between us. Okay, so here, let's make sure this makes sense. Grab your whiteboard tools, match these up again. We did this activity yesterday, so we're just trying to practice it again and again and make sure that we understand this. Go ahead, get your answers on the whiteboard. Oh, it looks beautiful. All right, I'm going to go ahead and pause in 5, 4, 3, 2, and 1. All right, let's shrink these down. Let's make sure this makes sense. We're going to go ahead and get my tool here so that I can highlight these. Awesome. So yes, conduction is when molecules collide because they're touching, and that's what transfers heat. Convection, remember, is how warm fluids will rise, cool fluids will sink, and that'll create currents. And radiation, again, carries energy without any matter by using electromagnetic waves. Give yourself a round of applause from the smiley face menu. You all did wonderful on that, and it was also very beautiful. So colorful. I liked the colors. Excellent. Okay. So we can see a picture here. We talked yesterday about a lava lamp being able to show all three of these, but in reality, most times when there's heat involved, you're actually doing most of these types of heat movement, okay? So we can see here that we're boiling some water, and so we've got our, what is this called? I forgot, our heating coil right here. Yeah, we have our heating coil right here. And remember that this is actually able to heat things that aren't touching it through radiation. So if you get close to the coil, right, you can feel the heat from it. Smiley faces if you know what I'm talking about. You're able to feel heat, right, from your stove without ever actually touching your stove. I don't recommend ever touching your stove when it's on, but you can get close and you can feel whether or not it's on. All right. Now, what's happening here is that, remember, yeah, if you touch it, you'll get burned. Exactly. If you see here, we can see that at the bottom of our fluid, we've got these hot molecules that are being heated up by our by our heating coil right here. And as they heat up, they float up, but the ones on top are cooler or cooling down, and so those ones sink and they're circling around, swirling around, and that is what creates convection, right? Convection currents. And then the other thing is that if you were to hold on to this handle for super long, you could actually end up burning yourself, right? Because remember, all materials, as they touch other hot materials, are going to get hotter because of the molecules colliding with this material. Okay, give me a smiley face if this helps you really understand the concepts we've been working on. Smiley faces if this makes sense. Good. Seeing them all together, hopefully we can begin to understand how they all work together. Now, the last thing that we need to review before we jump into our lab, because this is mainly what our lab is about, is conductors versus insulators. So remember, conductors will speed up the transfer of heat. And conductors are things like metals, aluminum, nickel, nails, keys, a jar lid. All of these things speed up the transfer of heat, right? That's why a lot of the time, our pans right here, our pots and pans, are often metal because it allows the heat to get from the heating coil to the pot and pan and through it to the food we're trying to heat up much faster. Okay, give me a thumbs up if that makes sense, right? Remember, they're good conductors because they transfer the heat very quickly. Awesome. Now, on the other hand, insulators, remember, are going to slow down the transfer of heat. So the opposite side of this is they slow it down a whole bunch. So things like wood, things like rubber bands, all of these things are going to slow down the transfer of heat. But remember, if I'm stirring with a wooden spoon in the pot and I just leave the wooden spoon in that like pot of liquid and let it boil away for a while, eventually is the wooden spoon going to get hotter? Will the wooden spoon eventually get hotter? Yes, absolutely. And the reason for this is because while insulators slow down the transfer of heat, they don't actually completely stop it. Okay, give me a smiley face if that makes sense. They don't actually completely stop the transfer of heat. Awesome, okay? So remember that eventually all heat will move. In the entire world, or the entire universe, there's no such thing as a molecule that isn't in motion. And therefore, as long as there's no molecule that isn't in motion, heat is able to move through those molecules. Okay, so taking a look right here, I want to remind you guys, why is this ice melting? Where is the heat going? Where is the heat going? Is it going into the ice cube? Is it leaving the ice cube? What's going on with the heat here? You think heat is leaving the ice. Okay, think about yourself. If heat was leaving you, how would you be feeling? If heat was leaving you, how would you be feeling? Yeah, you'd be feeling colder. In this case, it looks like our ice cube is melting. So if it's melting, it's getting what? Not colder, but what? Yeah, it's getting warmer, right? So heat is actually going where? Into or out of the ice cube? It's going into, right? If the ice cube is getting warmer, you need to be adding heat to it. Smiley faces if that makes sense. Okay, so we're actually adding heat, right? So we're adding heat into the ice cube. And what's that doing to our molecules? Is it making them slow down or speed up? If we're adding heat energy, are those molecules going to slow down or speed up? Think about you. If you chug some caffeine for energy, what happens to you? Yeah, absolutely. You totally speed up. And so as these molecules speed up, remember you can see that they begin to spread out and turn into a liquid. Smiley faces if that makes sense. Smiley faces if that makes sense. Again, how heat moves. Awesome. Now, what I do want you to notice here, okay, is that both of these ice cubes are currently on a hot plate, meaning a hot plate is a tool that heats things up. Okay, it's not like a plate that was in the microwave. It's an actual tool. So both of these are on a hot plate. Which of these is melting faster? The one that's directly on the hot plate or the one that is on the aluminum? Which one is melting faster? Yeah, it's a little bit hard to see, but the one on the hot plate is actually melting much faster. It actually already has some liquid next to it, whereas the one on the aluminum does not have liquid on it. Yes, exactly, Sophia, because right here on the left side, we actually get more direct heat. Okay, smiley faces if that makes sense. This one gets more direct heat. Okay, so remember on this side, technically foil is a conductor, but it's still an extra piece of material. So even though it's still a conductor, it's still going to take some time for the heat to get through it to begin melting the ice. Okay, so really the way that you can think of conductors is actually just bad insulators. Okay, conductors are really just bad insulators. Give me a green check if that makes sense. Conductors are actually just bad insulators. They're bad at keeping the heat away. Awesome. Okay, so that's going to be really important for what we're learning about today. Okay, so let's make sure that this makes sense. What I want you to do, grab your whiteboard tools, use the box tool, and I want you to go ahead and box the correct terms. All right, so conductors, do they slow down or speed up? Insulators, slow down or speed up? And heat, does that go from hot to cold or cold to hot? Go ahead, box the correct answers on the whiteboard. You guys have 30 seconds. So here we go, guys. Conductors are going to speed up the transfer of heat. That is definitely true, right? They make that heat go through it faster. Insulators, on the other hand, are going to slow it down. That's definitely also true. It will slow it down. However, I do want you guys to remember this. Heat moves. Which way does heat move? Let's talk about this once more. Which way does heat move? Look at what I'm pointing at right here. Which way does heat move? It goes from hot to cold. Remember, cold is not a real thing. So you cannot go from cold to hot because cold is not a real thing. Cold is just the absence of heat. You can only go from something that's hot to something that does not have hot, okay, to something that is cold. Smiley faces if that makes sense, okay? So right here, this one is incorrect. We need to go ahead and fix this one. It goes from hot to cold, hot to cold. Okay, again, once more. No, it's not a social construct. It's just, it's the way that we term things in everyday life, right? Because going like, oh, is it hot outside or is it absent of hot outside? Saying absent of hot outside definitely would get a little bit cumbersome. So saying, is it cold outside? You understand that cold is the absence of heat, right? Okay, perfect. This is number one in your attendance ticket. I'm going to give you 40 seconds to match those up. Oops, not 40 minutes, 40 seconds. Go ahead, work on that. Give me a green check when you have that ready to go. All right, waiting on Andrew's green check. Annalise, make sure I get your green check. Dalen, Libby, Eric, Haley, Michael, Tyson. So if we had boiling water, then put it in the freezer and it turned into ice, isn't that hot to cold? Yeah, so the hot air is going, the hot water, the heat is leaving the hot water and going into the freezer. And then how your refrigerator or your freezer works is it actually removes heat from inside of it and pumps it to the outside of it. That's why the back of refrigerators and freezers are hot, because they're actually pumping hot air out of them. Okay, so hot to cold, it's still hot to cold. Even though you're freezing an object, it's still going from hot to cold. It's removing the heat. Oh, that's not good. Oh my gosh, why? That's crazy. Maybe get a new fridge in that case. All right, guys, let's go ahead and keep on going. Oh, you're getting a new one. Awesome. Good, good, good. All right, so here is what we're talking about today in our lab. So we're taking a look at the types of materials that, sorry, say how it's in the chat box. We're looking at the types of materials that influence how heat is transferred. Again, we're going to be taking a look at things that are good insulators and things that are bad insulators. And then we're going to take that information and we're going to determine what materials would be good to make a thermos. So let's talk about this. How many of you have ever seen an insulated thermos? Take a look at this left side right here. How many of you have ever seen this? Smiley faces. Yes, exactly. How many of you have a thermos? Does anyone have a thermos? Yeah. Okay, now thermoses are super useful because of why? What do thermoses do? Tell me in the chat box. Why do you want a thermos? What is good about a thermos? Yeah, it generally, a lot of the ways that we think about it is it keeps things hot, right? So, for example, I oftentimes will make a bunch of coffee and put it into a thermos, and a day later, my coffee is still hot. Now, does that normally happen with regular containers, like with regular glasses? Does that happen? No. So the thing about thermoses is they're so cool because even 24 hours, they could keep something hot. Okay? So yeah, hot cocoa to sneak into class, exactly. I mean, sneaking it into virtual class isn't as impressive though, at least. But the other thing is thermoses can actually also keep cold things really cold for a long period of time as well. So the reason for this is because if we have a hot liquid, then the heat cannot escape the container. If you have a cold liquid, the heat can't enter the container and start to heat it up. Remember, because remember, heat is the only thing that can move. It's not that cold is moving, it's only that heat is moving. Smiley faces if that makes sense. Okay, so it's preventing the outside and the inside from interacting. Yeah, exactly, Mike. All right. Now, the reason thermoses work really well is because they're made of materials that help to insulate it. And again, insulation or insulators are going to slow down the transfer of heat. Both directions, right? They're going to slow down heat coming in. They're going to slow down heat leaving. So that's why it works for both hot liquids and cold liquids. So in our experiment today, we're going to take a look at a bunch of different materials, and we're going to decide which of these would be the best to design a thermos. What do you think we want for a thermos? Do we want good insulators or bad insulators? Do we want good insulators or bad insulators? What are we trying to analyze in our lab? Are we looking for good insulators or bad insulators for our thermos? Yeah, we're definitely looking for good insulators. So we want to find the materials that are the best insulators. Awesome. Now, what I want you guys to notice is over here on the right, we actually have what's an insulated water bottle. So an insulated water bottle keeps your water nice and cold for a long time. What I want you guys to notice is, what do you notice what's going on in this bottle? What does it actually look like is going on in there? Take a look at the two different colors here. What do you see with this bottle right here? You guys see the light blue and the dark blue? What do you see? Yeah, no. I know there's two different colors here. Yeah, exactly, Mike. It's almost like a chamber, right? Do you guys see how there's actually two layers here? You guys see how there's two layers here? Yeah, okay, so this is kind of crazy to think about, right? Because a lot of times if you see these water bottles, you're like, psh, I don't want that water bottle. It's taking away some of the space so that I can't drink more water, right? But what happens is exactly, Mike, this actually helps us keep our water cold longer. Now, the reason for this, okay, is because remember that solids have really close molecules, and so they can conduct heat much faster. Because remember, heat is the result of collisions, right? Heat is the result of collisions. And if molecules are super close together, they can send along those heat collisions very quickly. Smiley faces if that makes sense. Solids have close molecules, so it's like if you were right next to someone and somebody bumped you, you would immediately bump the next person. Awesome. Now, liquids are going to be more spread out, so they don't send on that heat quite as quickly, right? Because if you push them, it takes them a little bit before they bump into the next one. And gases are even more spread out. We can see this up here. Gases are so spread out that gases are actually pretty bad at sending on heat. So gases actually make really good insulators. Gases make really good insulators. Okay, so for example here, if you take a look at our bottle right here, what's happening is this layer right here, okay, might have a gas in it, or it might even actually just have a complete absence of air in it where there's nothing in it. But the whole idea is if there's nothing in here, or if it's just air in here, this means that it's even better insulated than if it was just the solid water bottle. Smiley faces if that makes sense. We add this little gap of air, or this little gap where there's no air. It could be either, all right? It could be a vacuum, right? Where it kind of helps to insulate even more. Yes, exactly, Mike. That's why regular plastic bottles are going to get warmer much quicker, because they only have the solid wall. They don't have a solid and a gas, or a solid and a vacuum insulating them. Okay, so let's go ahead. We're going to jump into our lab really quick. All right, it's a super easy lab. So I'm going to go ahead and open up the link. I'm going to show you what this looks like, but for right now, I'm going to send you the lab link. All right. Try to focus on what I'm doing right now. Okay, I don't want you to try to do it at the same exact time because you'll get confused. All right, but you're totally welcome to open that up, and you should be able to see what I'm seeing as well. Okay, so I'm going to go ahead and open up the virtual lab for you, and I'm going to show you how to get to the link to access the lab, okay, where we're going to actually do the experiment. Smiley faces if you understand what we're doing. Awesome. All right, so let me go ahead and set this up for us. All right, give me a smiley face if you can see my screen up here. Perfect. Okay, so what I'm going to do, I'm going to go ahead, we're in Unit 5, so I'm going to go ahead and navigate to Unit 5 since I know I'll find my lab in Unit 5. And then we're going to, once we're there, we're going to scroll down, and we're going to scroll down to 5E, right, because we're all the way on 5E. And you can see right here, here's the 5E lab. Okay, so you'll click on that, and you're going to click Start Lab. Okay, smiley faces if everyone understands that. I just sent you the link if you're in the live class, but for people who are watching the recording, I wanted to show that. Perfect, so I'm going to click Start Quiz and have that ready to go. All right, so once I'm in here, everyone, we can go ahead and underneath question 1 gives us the, question 1 gives us the link to where we actually do the experiment. So I'm just going to follow these directions. I'm going to click where it says click here, link to the virtual heat transfer laboratory. Okay. If it asks you to run Adobe Player, make sure that you click to run Adobe Player. If you're having any trouble with Adobe Player, please email me. I do have instructions on how to fix it in both Firefox and Google. So if you're having any issues, don't ever let that stop you. That's just an excuse, and we're not going to let excuses stop us from being successful. Okay, so if you have any issues, email me. I can help you out. Okay? All right, so I'm going to go ahead and click Begin the Lab. I'm going to put on my gloves. I always choose the green ones. I feel like they're the best looking gloves here. And click Start. Okay, so here's our lab right here. So we can see on the left we've got some materials. Sorry, let me blow this up a little bit. We've got some materials on the left: aluminum, glass, fiberglass, air between glass, and brick. Over here we've got some tongs that'll allow us to pick up all of our materials and our ice. We've got some ice over here. In the center we have a hot plate that we can turn on and off. It's on when the red light's on, off when it's off. And then over here we've got a timer, right? We can start it, we can stop it, we can reset it to 0. Okay, smiley faces if you understand what we've got in our lab. If this makes sense, if anyone's confused about this, make sure you let me know. Good, all right guys. So we've got our lab open. Let's see what we need to do next. So I'm gonna jump back here. Okay, so we've got our lab open. All right, so what we need to do is we have a really small table that we need to fill out. And guys, this is so easy, okay? I'm not kidding. This is so easy. It's much easier than Tuesdays. It's actually much easier than all of your labs that you've done so far. Okay, you just need to get 5 results. So all you need to do is you're going to take your tongs, you're going to place one of the materials onto the hot plate. We're going to put an ice cube on top of it, start the hot plate, and start the timer. And we're going to wait for the ice to melt, and then once it's melted, we're going to stop that time and record the time in our table. Okay, and then we're going to repeat this with the other materials. Smiley faces if that's starting to make sense. I'm going to demo it for you in a moment, but I want to make sure that that makes sense kind of briefly what we're going over. Okay, no worries, Ariana. I'm going to go over it step by step now, okay? So let me go ahead and show this to you again. So again, the instructions, guys, are actually right here for you. Okay, so it says use the tongs to place the material on the hot plate. And again, we have 5 materials, so I can use any material right now. I'm going to start with aluminum just because that's the order that it goes in my data table. Okay, so I'm going to grab the tongs, grab the aluminum, place it on the hot plate. Okay, smiley faces if we understand what I did so far. We're following along. Oops, sorry. Good. Okay, now I'm going to grab some ice. I'm grabbing some ice. I'm going to place that on top of the aluminum and drop the tongs. Okay, so I've got my material, I've got my ice. Now, we're going to turn on the hot plate. Let me zoom into this. We're going to turn on the hot plate and the timer at the same time. This is the instructions, Brianna. You don't need an instruction video because the instruction video is literally what I'm telling you right now. So if you need this again, it'll be in the recording. Okay, so we're going to turn on the hot plate and turn on the start timer at the same time. So 1, 2. And we're going to wait for the ice to melt. Smiley faces if you see the ice melting. It's disappearing. Okay, as soon as it completely disappears, I'm going to click the stop. And stop. Okay, so you guys see right here, this is 18. All right, do you guys think this is 18 minutes? Has 18 minutes passed? No, this is actually 18 seconds. Remember, right here, this is minutes. The first number is minutes, the second number is seconds, and the third one is going to be milliseconds. Okay, smiley faces if that makes sense. Minutes, seconds, milliseconds. Okay, so I'm going to go ahead, I'm going to take this and I'm going to put it into my data table. So I'm going to go back over to my lab right here, scroll down, and here's your data table. I already made your data table for you. You just need to enter the number, and my number was 0 minutes, 18 seconds, and 0 milliseconds. Okay, so I've recorded that. Let me blow that up for you just so you can see that. Okay, make sure you do this on your own. Your melt time will be different. Okay, so you need to make sure you use your own data, just like always. Don't cheat, use your own data. Awesome. Let me explain that once more. You just need to enter the actual number as you see it, Ariana. So you would enter 00, 18, 00. But I can show this to you once more, okay? That this first number is minutes. The second number is seconds. And the last number is milliseconds. Okay, smiley faces if that makes sense, guys. Literally, you guys saw it melt. You know it was only seconds because you saw it melt. We didn't just sit for 18 minutes waiting for it to melt. Awesome. Okay, so let me go back here. I'm going to do one more example. Do we feel like we'll be able to do it once I do one more example? One more example and then we'll feel good about it? Okay, good. So I'm going to go ahead. I'm going to remove this material and drop it off. I'm going to grab the next one, which is glass, and drop that on. I'm going to grab my ice cube. Oh, sorry. Really important, guys. Totally forgot. Totally forgot. We got to reset everything. So reset and turn off the hot plate. Annalise, make sure that when you are grabbing, you're using the tongs. And to grab the tongs, you have to go over to one edge and you'll see the fingers spread out. Okay, so once the fingers spread out, you'll be able to pick up the tongs. Yep, no worries. Okay, so we're going to grab the ice cube, drop it on top. Again, my hot plate's got to be off. Otherwise, it's going to start melting before I can turn on the timer. Okay, so we're ready. I'm going to zoom in. I'm going to press this and the timer at the same time. So 1, 2. We're going to watch it melt. Okay. Now this one is melting. Is it melting as fast? No, it's definitely melting slower. So what do you guys think? Is glass a better or a worse insulator than aluminum? Is it a better or a worse insulator than aluminum? Is it better or worse at slowing down heat? Yeah, it's definitely a better insulator. So we're going to see that this is definitely going to be more time. All right, so this would be a better material for our thermos. Maybe not the best. We still have to test out the other 3. But so far, we know that this one's definitely better than aluminum. Smiley faces if this makes sense. This one's definitely a better material for our thermos. Awesome. All right, it's almost done. I'm going to go ahead and, oops, hello. All right, melting, 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 melting. Come on, melt faster, ice. Anyone got a joke while we wait? All right, it's almost done. No jokes. Come on, guys. Knock, knock. Who's there? Oh, and we're done. So 1 minute, 24 seconds, 62 milliseconds. So I'm going to go ahead and write that in. So 0, 1, 24, 62. Oops, 62. Is that what it was? Yeah. Okay, so smiley faces if you understand what you need to do. You're going to have to repeat that with fiberglass, air between glass, and brick. Okay? So once again, make sure you turn everything off and reset everything before you do your next ones. Okay, so we'll remove this one, and then we'll do fiberglass, and so on and so forth. Okay, until we've got all of our measurements. Okay, so give me a thumbs up if that seems super easy, thumbs down if any of that is confusing. I know, this one is a really easy lab. Awesome, guys. So once we have that, make sure you save your results. And then all you need to do is for the last 2 questions, we're going to go ahead and analyze our data, just like always. So for the last 2 questions, you're going to start with what's the least insulating. So for example, aluminum is definitely going to be on the lower side, right? So this one might be aluminum, it might be number 2, but it's definitely going to be less insulating. And on the other side, we're going to have the most insulating, right? So glass is definitely going to be a higher number than aluminum. Smiley faces if that makes sense. Glass will definitely be a higher number than aluminum. Awesome. Okay, so go from least insulating to most insulating based on your numbers here. Then the last question asks you, what are the 2 best materials for an insulated container? It turns red. Okay, so the button turns red to turn it on. Okay. So for this last question, all you need to do is you need to look at number 4 and number 5, right? So the number 4 and number 5 are going to be the higher end of insulation. And so those 2 materials are going to be better at insulating, right? So we want to look at number 4 and number 5, okay? Don't type this, guys. Make sure you type a real answer. Type a real answer, okay? Remember, use complete sentences, use your own words. And the last thing I want you to do is I want you to tell me the data, okay? So tell me what 2 materials are good and tell me why are they better. Tell me what numbers did they have that showed you that their numbers were better than the other materials, okay? And that's it. Give me a smiley face if number 2 and number 3 make sense. Smiley face if number 2 and number 3 make sense. Okay, it's a super easy lab, guys. You should definitely be able to get all 15 points and get them easily. And this is really good because remember, labs are 25% of your grade. So an easy lab, we got to take it, we got to rock it because that's going to help boost our grades quickly. Okay, awesome. So let me stop that. I'm going to go ahead and jump back over here. So again, make sure you answer number 2 and number 3. Okay. So here's our objective for today, right? We talked about heat, conduction, convection, radiation, and we talked about conductors versus insulators. So what I want you to do, on the last slide in a moment, I'll give you your last word, and you're going to do your attendance ticket and submit that. However, you will need to do the data collection for the lab on your own. Should not take you long, might take you like 20 minutes to get that done. Submit that, it's due by 4 o'clock, but remember, if you can't get it done by 4 o'clock, still turn it in so that you can get your full credit. Even if you turn it in late, you'll still get full credit. It's much more important to me that you do it correctly, okay? I don't want you submitting garbage labs because that's super disappointing to me. I much prefer you to do it well and turn it in when it's done well. Smiley faces if you understand. Yes, higher time is more insulated. Absolutely, Santa. That's a great point here. Let me type this up here so we have it on our recording, right? So higher number is more insulating, okay? So number 4 and number 5 are what are the best 2 materials, okay? So higher numbers right here and the best 2 materials that we talk about down here, okay? Awesome. All right, here you go, guys. Here's your last word. I hope you have a wonderful day, and I will see you all later. Bye, everyone.